Okay, let's look at power series with this lesson. And if you want to print a guided notes sheet, you can go to this bit.ly link and print something to follow along if you want to do that. My students should already have a hard copy of that. And so let's talk some terminology first. A power series is an infinite series, only this time we have something in addition to the n's that are going from 0 to infinity. We also have this x minus c thing being raised to the n power. And in these series, x is a variable, and c is called the center of the series. We'll talk more about what the center means and how we're going to use that. When you're reading these, you can read it the power series n x minus c. You can call it the power series about x equals c. I prefer to call it the power series centered at c because that reinforces the fact that that is a center. And then what we want to do generally with a power series, among other things, is we want to find out what makes these series converge, and that's going to be dependent on the variable x. So what are all of the values of x for which the series converges? And that's what we're going to have to figure out. A little bit more terminology. We have the radius of convergence, and the radius of convergence, going back to the idea here of the center and looking for all the x's that the series converges for. The radius is the distance you can travel from the center and still be convergent. So we're trying to figure out from the center, how far can I vary and still converge? What values of x can we plug in that makes the series converge? The interval of convergence is listing all of the x's for which the series converge. Those sound pretty similar. Just remember, radius is simply a distance. The interval is actually the x value, and you would put that, the interval of convergence, in either interval notation or set notation. And the way we're going to determine that most of the time is by applying the ratio test. So there's going to be a lot of pencil to paper time for most of these. However, if you happen to notice that your series is a geometric series, if you have a geometric power series, then we can cut back a lot of the work because every geometric series will strictly only converge if your ratio is less than 1. So if you see a geometric series, find the ratio of that series and then determine what makes that ratio less than 1. We'll find all the values of x that will do that for us. So let's look at a few examples, and before I dive into the ratio test, I'm always going to stop and wonder, is this a geometric series? This one is not. It's x minus 3 to the n over n. That over n is screwing up the geometric series. I am going to go ahead and make a note that the center of this series is x equals 3. You can call it c equals 3 if you want to. And so I'm going to draw a number line here for a second, and I'll explain why in a minute. I am centered at x equals 3. So there's my center. And I'm going to go ahead and set up the ratio test, and I'm assuming you know how to do the ratio test, so I'm going to go ahead and have those set up already, and I will have it reduced as well. As a matter of fact, here's the reduced version. And I tell my students, and I'm going to reinforce this for mine who are watching this, do not, if you are an AP calculus student, I would encourage you not to physically cross things out. While it feels good, and I like to cross things out so I can see what's left, what you need to remember is on the AP exam, they scan your work, and the scan quality is not always great. It's good, but it's not perfect, and you get a point for the setup. So on the AP exam, if you have to do the ratio testing for your response, you almost always get 1 point for setting up the ratio correctly. And if you're really heavy-handed in scratching it out, it's going to be hard for the reader to see that setup to give you your point. So I'm encouraging my students to not physically cross things out and try to get to where you can cross things out mentally and preserve that initial setup. So on to the limit. I need to find the answer to this limit, and do remember this is a limit as n goes to infinity, and for my n terms I have the same degree on top and bottom, which means I can divide their coefficients, and the coefficients are absolute x minus 3 and 1. And then for the ratio test, we're trying to figure out what makes this converge. The ratio test shows convergence when your answer to the ratio, when your answer to the limit is less than 1. So before I finish solving this, I'm going to make 1 point. When you get to the point in your ratio test, you're going to do all this work. You will eventually get to where you have x minus the center is less than some number. And when you get to that point, that number is the radius of convergence. So right now, I know the radius of this one is 1. So the radius is 1. Now going back to my number line up here, that tells me that from my center of 3, I can go 1 unit to the right, which takes me to 4. I can go 1 unit to the left, which takes me to 2. And I know I'm going to converge for all x values between 2 and 4. Now that's one way you can solve the inequality. Another way is you could actually just channel your algebra brain, right? So you should have learned how to solve these a long time ago. If absolute something is less than 1, I need that something to be between -1 and 1, and that's going to happen when x is between 2 and 4. Okay, so again, the interval that we have right now is 2 and 4, but keep in mind that if x is equal to 2 or if x is equal to 4, then the answer to this limit is 1, and the ratio test is inconclusive when when the limit is 1. And so what we have to do, and this is one of the annoying things about using the ratio test, which we're going to have to do most of the time, is we will have to manually check each of the endpoints. So I'm going to have to wonder, what if x is equal to 2? What series will I get? So go back to the original series. If you plug in 2 minus 3 is -1 to the n over n, and that is your alternating harmonic series. That's going to converge. So we will converge at x equals 2. So I'm going to draw like a little bracket at 2. I'm going to include that one. And then if x is equal to 4, my other endpoint, I have the series 4 minus 3 to the n, which is 1 to the n over n, and 1 to the n is just 1. That's your harmonic series. That's going to diverge, so we will not include the 4. And so there's the answer to the interval of convergence. We already knew between 2 and 4. We knew that a long time ago, but now we know that we will converge also at 2, but not 4. And I'm going to drive the point home here by actually labeling my interval of convergence. And I'm being a little bit lazy. I guess I'll write the word convergence. The interval of convergence is including the 2 and not including the 4. So there is one example of using the ratio test to find your radius and interval of convergence. Let's look at another one. And before we set up the ratio test, ask yourself if this is a geometric series, and this one is not. So we will once again set up the ratio test, which is set up right here. And this one's kind of nice because that's not a fraction. So n plus first term over the nth term, start reducing that. The x's, I have one more x on top than on bottom, so I'll have an x in the numerator. The factorials, n factorial will cancel all but the n plus 1 in the numerator, and so your reduced version is this. And this is an interesting one. This one's going to be a lot faster than the first one, because this series, if you want to think about degree on top and bottom, this is over, the top degree is bigger. This is blowing up. This is going to, I'm going to say equals infinity. I probably shouldn't do that, but I'm going to say equals infinity. Well, that's a little bit bigger than 1. Therefore, this diverges. This series diverges for all x, but not quite. But not quite. And because there is one place that I can make this thing converge, and that is at the center. If I plug in 0 for x, now it would be a really silly series, but it's the sum of a bunch of zeros, right? So if x is equal to 0, have the sum of 0, and if you add a bunch of zeros together, you're going to get 0. So this series will diverge for all x that are not equal to 0, which means the series converges only at x equals 0. So there's not really an interval of convergence. There's a point of convergence. The radius of convergence is 0. That is horrible penmanship. Goodness. The radius of convergence is 0. And the main point that I want to drive home with this one is every series will always converge at its center. Every series will always converge at its center. So if you do get a blowing up limit, remember that the center of the series will result in a bunch of zeros and it will converge. Now let's look at this one. Again, I'm wondering, is this a geometric series? And it almost is. I'm going to show you this just for the sake of making a point. If this root n was not here, then I could rewrite this series as the quantity x minus 2 over -2 to the n power, and that's a geometric series with the ratio of x minus 2 over -2, and I know that will converge when the absolute value of that is less than 1. And the advantage to geometric series is that for the geometric series, we know the series will diverge if the ratio is equal to 1. We don't have that inconclusive equals 1 situation like we do with the ratio test. So if you can use geometric series, do that. But since this one's not a geometric series, let's get rid of that. Let's bring the root in back in, and we will set up the ratio test. So here's my ratio test, a little bit uglier. And again, I want my students to reduce this without physically crossing things out, because I want it to scan well for the AP exam. And when you reduce this, you will end up with this expression. And so I'm looking at my degrees on top and bottom, and I'm using the word degree loosely because these are not polynomials, but it's into the 1/2 on top and bottom. The answer to the limit is going to be the quotient of their coefficients. So we have absolute x plus 2 over, and I could have gone ahead and absoluted the -2 and just put a 2 down there. I'm going to do that at this point. And something else that I blew through earlier, and I didn't stress this, I probably should have. This is the downfall of having things pre-done for the sake of speed. When you address the absolute values, because you're going to have to think about what the absolute values can impact when you're reducing your ratio, n and n plus 1 are already positive. So you'll notice I left those out of the absolute values because those are already positive. Absolute value is not going to affect that. X minus 3 might be negative. We don't know what x is, so if x is small enough, x minus 3 could be negative, and therefore we keep the absolutes around the variable expressions. So just kind of think, can this thing be negative? If so, the absolute value matters. Did the same thing on this one. The n plus 1 is positive, but the x might be negative. This one, the root n expressions are positive. I could have gone ahead and absolutely valued the -2 and just written a 2 down here, and then x minus 2 needs to stay in parentheses. I'm sorry, in absolute values. And now, once again, I'm going to solve this. I need to know when is the answer to that limit less than 1, and that's going to happen when absolute x plus 2 is less than 2, and there's my radius. So I now know my radius is x equals 2, and going back to the number line approach, which is kind of like what I like to do, I'm centered at -2, so there's my center, and I just found out my radius is 2, so I can go 2 units to the right, that takes me to 0, I can go 2 units to the left, that takes me to -4, and I know I'm going to converge at least for all of these values between 0 and 4. I now need to test 0 and 4. So I'm going to test what if x is equal to 0 and 4, -4. What if x is equal to -4? I would have the series -4 plus 2 is -2 to the n over -2 to the n times root n. The -2 to the n's cancel, and we have just 1 over root n, and that is a p series where p is 1/2. That diverges. So we will not include the -4. So we're not including that. What if x is equal to 0? Now I have the series of 0 plus 2, which is 2 to the n over -2 to the n, root n. And 2 to the n over -2 to the n can be written as -1 all to the n over root n. And that is an alternating series. And if you did the alternating series test, the 1 over root n does decrease in magnitude to value, it does decrease to 0. Therefore, this is going to converge by the alternating series test. And so I will include the 0, and I now know my interval of convergence is. So we're going from -4 to 0. We are not including the -4. We are including the 0. And make the parentheses and brackets really obvious so they don't get mistaken for the other one, for what you didn't mean to write. That came out really clunky. Okay, so number 4. Last one that's going to need the ratio test. And again, it's not a geometric series, so I can't go with the geometric ratio. So we set up our limit, the n plus first term times the reciprocal of the nth term, or divided by the nth term. And I'm looking at what can cancel. Let's see, the x plus 4s, I'm going to have 1 x plus 4 remaining in the numerator. The root, the n factorial, and the n plus 1 factorial will leave an n plus 1 in the denominator. And thinking about the absolute values, the n is always positive. That x plus 4 that's remaining on top can be negative, and so it reduces to this. And so we have the absolute value of x plus 4 over n plus 1. And this is a neat one because this one's bottom heavy. If n is going to infinity, if n is going to infinity, my bottom is blowing up, but I have a constant, x is like a constant for the limit. On top, this limit is 0, which is beautiful. This is what you really want to happen because it really cuts down on time. This limit is always less than 1. I don't have endpoints. This converges always. Does not matter what we plug in. Converges for all x. And so your radius of convergence is infinite. And the interval of convergence would be all real numbers. So there's number 4. And then I have one more that I want to look at over here. And that is this one. And so I've given you a generic series. I just called it a sub n times x minus 3 to the n. I tell you this series converges at 5 and diverges at 6. And then we're trying to determine for these x values, will the series converge, will it diverge, or do we not have enough information to determine that? And the best way to do this, there may be other ways, but I like to go ahead and graph everything that I can on the number line like I was earlier. And I'm noticing that the center of this series is 3. So what I'm going to go ahead and do is I'm going to draw a number line. I'm going to have 3 in the middle, and then I'm going to think about all of these other values given. And so here I am. There's my number line. I'm going to make a note that 3 is the center. 3 is the center. And then I'm looking at some other stuff. I know we converge at 5. So we're converging at 5. We're diverging at 6. So we're diverging at 6. And that tells me if I'm centered at 3 and I'm converging at 5, that tells me that my radius is at least 2, right? Which means I can go 2 units this way, and I know I'm going to converge for everything between -1 and 5. So knowing that, I can go ahead and say that we're going to converge with absolute certainty at x equals 2. And none of the other questions are between 1 and 5. We do know we're diverging at 6. And so if we start diverging at 6, maybe we converge all the way up to 6. Maybe we're still converging at 5.5 and 5.8 and 5.9. So it's possible that the radius is 3. So my radius is at most 3. And if I'm already diverging at 6, that means I know I'm diverging everywhere after 6. So we can go ahead and say that we know we're diverging at 8. And if my radius is at most 3, I can go 3 units this way. And I, again, know I'm diverging everywhere. Whoops, diverge? I know I'm diverging everywhere over here, which there's -1 and -2. Both of those are going to diverge. And then we have x equals 1 and x equals 6. I don't know why I gave you x equals 6 to think about, because 6 is given in the information, so I guess we'll go ahead and label that diverge. And then x equals 1. What do you think about that one? We were converging 2 units to the right. Does that mean we converge 2 units to the left? Maybe not, because if the radius of convergence is exactly 2, then I would need to find a way to test that endpoint, and the information we have doesn't give you enough information to be able to test that endpoint, so we don't know. Not enough info. And so there we go. That is the end of this lesson, and hopefully that makes some sense to you.